Hello everybody, thank you for joining me today. My name is William and today we're going to be covering ultrasound. So some of our learning objectives include what actually is ultrasound, how does it work, and what are some uses of ultrasound. Now, some things you should already know are the fact that the speed of sound varies in different mediums. If you're not too sure about this, go back and watch my previous video on sound and you'll understand this. So let's get right into it. Okay, so now we want to understand what actually is ultrasound. Ultrasound is merely any sound with a frequency greater than 20 kilohertz. So any sound with a frequency above the human hearing range, above 20,000 hertz. Now, how do we actually use ultrasound in the real world and where do we use it? So all ultrasound applications in the real world follow the principle of echolocation. Now, if we break this word down, echo meaning reflected sound and location meaning where something is, you can sort of get an idea of what this actually means. This means using the reflected sounds of an object to find out where it is. So some use cases in the real world that we can apply this to are baby scans. We can also use this to detect cracks in pipes. And we can also use this to image the Earth. So look at what's happening underneath the Earth's crust. Image the internal of Earth's crust. Now, how does echolocation work in a diagrammatic form? I'm going to explain to you now. The biggest pro with using ultrasound as compared to some other methods such as CT scans or X-rays is that it's non-invasive and it's non-ionizing. So you don't actually have to break open anything, so you don't have to cut open the baby out of the womb to inspect it. You don't have to dig up pipes out of the ground. You don't have to dig up huge amounts of the earth to image its internals. Also, ultrasound, seeing as it's actually just sound and not ionizing radiation, which is the harmful kind, we don't actually affect whatever we're imaging. How does ultrasound actually work in action? As you can see here, I've got a baby in a womb. I know I'm not going to win any art awards, but oh well, we're doing physics here, not art. So the ultrasound transducer here, so that's a specific physics word that you need to know. It's called a transducer. This means that this device here can both send pulses and receive them, and it needs to be able to do that, and you'll see why in a moment. This transducer here sends out a pulse, and this pulse hits the child and then is reflected back to the transducer, and that it picks up. Now, this transducer thus produces a chart that looks kind of like this, right? I have pulse along the y-axis, and I have time along the t-axis. The initial pulse that the transducer sends out comes out like this, and then you have another pulse later on, which is a lower peak because some of it gets absorbed by the actual child, but it doesn't actually harm it. That's reflected back. Okay, so let's say that this is the sent and this is the echo. Now you can see why it's called echolocation. Say this is time t1 and this is time t2. Okay, it could be, this is usually done within milliseconds, even microseconds, but let's just stick to t1 and t2 right now so we don't get bogged down with the numbers. Now, the time difference between these two is as follows: t2 minus t1 is equal to delta t, because remember delta is the Greek symbol for change in. Now, delta t is the time there and the time back. So if I just do t1 and I do t2, we want nothing that we know is the speed of sound within the womb. The womb is mostly water, so we can just say speed of sound in womb. In a previous video, I said the speed of sound in water is around 1600 meters per second. Let's just stick with that. Now, we have the time that the transducer gives us due to the two different peaks, and also we have the speed. Now, using our distance equation, we can just do speed is equal to distance over time. But remember, we're working with velocity and displacements here, because remember, we want direction, we want distance with a direction. So we do velocity is equal to displacement, which has an S, which is a bit confusing. Velocity equals displacement over time. Now let's rearrange this for displacement, which is Vt equals S. Okay, now we have this, but our time is to the baby and back. We just want the time to the baby, right? Because we want displacement, direction, and distance. So we multiply it by a half because we only want half the time it takes, which would be the time to the baby. So here is our echolocation equation. Echolocation equation. Now, some common mistakes are, and like you might have noticed me emphasizing this so much, that you have to use half the time, which is the time to the object. That's a very common mistake that students make, to use the whole time. Don't do that. Also, you might see this example being given as like a baby scan, or you might see cracks in a pipe, or you might also see deep sea fishing, which is actually a very common one, and that actually came up in my GCSE exam. So I hope you understand this now. If you do, you understand echolocation and ultrasound. Well done. Now let's have a look at our worked example. As always, we're going to read through and we're going to highlight all of our keywords. Ultrasound is used to scan metal pipes to measure their thickness. Okay, the ultrasound wave travels through the metal and is reflected at the inner surface of the metal. Let me make the highlight a bit thinner. The reflective wave is detected after 0.03 milliseconds, and it's given that in real seconds as well. The speed of ultrasound in metal is 5,000 meters per second. Calculate the thickness of the metal. Okay, so let's draw a quick diagram here just so we understand exactly what it's saying. We can see that there's a tube here, like that, and we're seeing ultrasound pulses are being sent in and they're being reflected, and we want to know the thickness T there. Alright, so that's really just the distance between the outer ring of the pipe and the inner ring of the pipe. So let's start off with writing down our, actually we don't need to write that in the equation because the equation is given to us. So let's just start using it straight away. We know that the reflective wave is detected after 0.03 milliseconds. The reflected wave there and back. So we just need half the time, right? Because we only want to know how long it took to get from the outer ring to the inner ring. So we do 0.003 milliseconds. So that there's 1,000 milliseconds in a second. So we can just do times 10 to the 3 here, or you could just do divide by 1,000. Doesn't really matter. Over 2, and that gives us 1.5 times 10 to the minus 6 seconds. So that's how long it took for your ultrasound pulse to just get there, to get towards the inner pipe, to travel the thickness of the pipe. Now, the distance is just the speed multiplied by time. So all we do is 5,000 multiplied by 1.5 times 10 to the minus 6, and that is equal to 7.5 times 10 to the minus 3 meters. Now you have to remember all of units. Although it's given there in your answer line, sometimes it isn't, so you have to be careful. So that's our answer right there, 7.5 times 10 to the minus 3 meters. And that is 3 marks there. So if you understand this, well done. If you don't, keep trying more questions, you'll understand it soon enough.